So yesterday we stopped at the bearing capacity problem, and then today we are going to go further to consider the impact of groundwater on the bearing capacity of foundations. So it's like by considering groundwater level, it kind of adds another level of complexity to the problem. But you find out that it's actually quite essential, because most of the time when you are working in the field, you will experience some sort of groundwater. Like typically what we are doing earlier was mostly dry soil condition. Maybe probably is the dream of every engineer to face that type of situation in the field, where everything is so simple and straightforward. But in reality, that's not the case. You have complex situations like this one. But actually, they may seem quite complicated, but if your fundamentals are quite strong, they are all very, very similar. And then if you start doing it, you will realize that like you still are going to use the same sets of equations. It's just that there will be a little bit of modification, or some modifications depending on the condition we are dealing with. For example, when we are considering the effect of groundwater on foundations, it's like you have three different types. For example, here we have case 1, case 2, and case 3. So this one here is case 1. So for example, we have a case 1. So this is the strip footing, like this. Okay. And then you probably have your water level here. Okay, so typically for case 1, you will have some sort of a problem like this. This is the ground level, and then you have the foundation base, but the groundwater level is a little bit above the base of the foundation, so you can see it here. So typically that is what they are trying to describe in this figure. That is the figure number 1. And the good thing here is that in order to determine the bearing capacity of this type of problem, we are still going to use this same equation. But the difference is that some of the factors you will consider here will be different, a little bit different from the previous ones, like when you are dealing with the dry soil conditions. Okay, if we look at this, like the C factor here, it's like cohesion, right? And then this Q is due to the stress at the base of the footing here, right? From the surcharge loading above. And gamma is like the unit weight effect. Okay, the gamma effect, the Q effect, that's the stress effect, and the cohesion effect. But actually, if you look at all these parameters here, there are only 2 parameters that are affected by the groundwater level. And those 2 parameters are this and this. They are the only parameters you need to pay attention to. Everything else remains the same. Like these ones, how you calculate them remains the same, like the previous one. This one also the same. These ones are all the same. Only this and this will change. So, and then that is also the major difference for each of these problems. Like for example, case 1, case 2, and case 3. How you evaluate this value for case 1 is different from case 2, and it's also different from case 3. So that's why you need to have a very good understanding of the fundamentals before you'll be able to solve this type of problem. So for example, if you have a problem like this, right, and let's assume there's no water level. If we want to calculate our Q, what we say? We say Q is equal to what? Gamma F, right? The depth of the foundation. Typically, that's what we do. But now that we have the water level here, so we cannot do that anymore. Our Q, we have to calculate it in a different way. How do we do that? So it's going to be gamma 2 multiplied by this plus, because this gamma is below the water level, right? So we need to gamma 1 minus okay, so that's how you will get the Q in this case. This gamma multiplied by this D2. What is D2? It's just dF minus D water. That's the depth of the water level, right? Which is from here to here. And then you just multiply this gamma. Or this one you subtract the gamma water. Why? Because it has to be the effective stress analysis, right? So you minus the water. And then you multiply by D1. So that's how you get this one. Okay, and for our gamma in case 1, if we are going to find our gamma, we are just going to say gamma equal to gamma 1 minus this, okay, which is the effective yield rate, okay, or gamma prime, gamma 1 minus this. So this gamma 1 in this case will be what? The gamma saturated, right? Because it is below the groundwater level. So you can write gamma 1 here, or if you want, you can substitute it with gamma saturated. Okay, so typically for case 1, this is all you need to remember. How do I evaluate the Q? And then how do I find the gamma? Okay, this is the approach. Because the base here, and then the water level, the foundation base is already below the water level, so use the gamma prime, which is the gamma saturated, gamma 1 minus gamma W. And then Q, if you look at this, you want to calculate the stress, effective stress, this times this, plus this minus that, times the depth from here to here. Okay, and typically for me, before I solve this type of, yes?
Gamma water for water is 9.812, right?
Yes. Yeah, gamma W is 9.8. Okay, so typically for me, like usually when I solve this type of problems, what I will do is like, first of all, I will identify, okay, is it case 1, case 2, or case 3, and then just find this and this, because you already know how to determine these other values, which are quite easy. So the only values you need to pay attention to is this and this one. Okay, so any questions about how to calculate the stress, that is the Q at this point, and then also the gamma that we use to substitute there? Any questions? Fair enough, right? Okay, so later we will also have an example that we can go through, and So here, this is our example. So the foundation is so the footing is okay. So by looking at this problem, these are the parameters that we need, right? And then we also get this gamma and this one. We have 18 and 20. Okay, let's see. Okay, so the depth of the foundation here is 1 meter, and the water level is at 0.5. So let's say it's a little bit higher. Okay, the depth of the water level. So in order to solve this problem, let's see, we have to find the QU, right? So first and foremost, we are dealing with sand, and typically the collision will be 0. So that one is already given there, right? C equal to C prime, which is 0 when we are dealing with sand. And then you have the frictional angle of 32. Once we get our frictional angle, then we can get these values from the table, right? The table from earlier, like the phi prime of 32, NQ is 23.18, 35.49 from here. Okay. 32, so we get the values, those values from here, NC, NQ, and N gamma. So we just write those ones down here. And then we can find the shape factors, the depth factors, and the inclination factors. So even with the presence of the groundwater, you will realize that this process still remains the same. How you evaluate this, nothing changes. It's still the same, nothing changes. The only thing that will change is how we evaluate the okay, so you see, it's the same values. The FCS, FQS, the shape factors, the depth factors, the inclination factors are all the same. But the only difference is they first had to calculate the Q and the gamma, that is the stress. So that's where the differences come into play. So if we are going to find the Q at this point, right, as we stated in the above example, what do? It's going to be this gamma 2. Our gamma 2 in this case is 18. So 18 multiplied by the depth from here to here. Because you know here is 0.5, so here will also be 0.5, right? So that means we already know the stress from here to here. Now we have to find the stress from here to here, and then that will give us the stress at this point. And then how do we determine that? We use the effective stress, right? We say 20 minus 9.81, and then you multiply that by the depth here, which is also 0.5. Okay, so that's how this comes about. 18 multiplied by 0.5, 20 minus 9.8 multiplied by 0.5. So that's how you get your Q at this point. Okay? And then for the gamma, you are going to use the gamma side. So it's the gamma at the base of the foundation. We have two gammas. We have 18 and then we have 20. But this foundation is on the soil layer in which the gamma is what, 20. So we have to use that one. Okay, so we say gamma will be 20 minus 9.81. Okay, and then you also get that value for your gamma. So once you get these two values, the gamma and the Q, since these ones are the same as the previous values we get earlier, you just substitute in your equation and then repeat the same process. And then you will get exactly the result as it is there. So the only thing here is that you need to remember that if you are going to use this type of, or if you are facing this type of problem, then you have to use the effective, if you are using the effective stress method, then you have to remember to subtract the gamma W, okay, below the water level. Okay, so you get everything there, substitute in the equations, and then it's quite straightforward like the previous ones. Okay. For case 1, do you have any questions before we move to case 2? It's the process is not that complicated. It's just that there are so many things that you need to remember. But once you familiarize yourself with the fundamentals, then it is actually quite straightforward and easy. Okay, so if there is no question, I think we can look at case 2. Okay, so case 1 here, right? We mentioned that case 1 here, we mentioned that the water level is above the base of the footing, right? But for case 2, the water level is a little bit below the base of the footing, okay? So at this point, we should not ignore this water level here because it's not deep enough. You may probably say, but it's below the foundation. I don't need to consider it. But the depth from here to here is not big enough for you to consider, for you to ignore it. So it says, if the depth of the foundation is less than the depth of the water level, so that means the depth of the water level is larger, but this depth of the water level is actually less than this plus this. Okay, so that means if the dW is less than dF plus P, that means the groundwater level will still impact the foundation. Okay, so this is also one of the conditions. dF is less than this, but dW is also less than dF plus P. Okay, so similarly to case 1, the only things that change in our equation are the surcharge and the gamma. For case 2 also is the same thing. The only things that will change is this, and this, okay? Why? It is because of the location or due to the location of the water level. So let's quickly okay, so let's say we have a problem like this. Okay, so okay, so if we have a problem like this kind of a problem, so we have this, the depth of foundation, case 2, and the water level is located somewhere below the foundation. Okay, but as we mentioned, this depth is less than this plus this. Okay, so if we are going to find the stress at this point, what do you think the stress will be at this point? At the F. What will it be? Do you have an idea? In terms of, okay, let's say, so if you are going to do in terms of Q, or the stress at this point, can you make an assumption like, how do you think we can calculate the stress at this point? It's actually quite straightforward, because if we are going to calculate the stress, what do we say? It's the unit weight multiplied by the depth, okay? So from here to here, we have only one unit weight. What is that? Gamma 2, right? So it's the unit weight from here to here. So we just, to calculate this, we say gamma 2 multiplied by what? dF. Okay. It's actually quite straightforward for that one. Okay. So in terms of Q, it's going to be gamma 2 multiplied by the depth of the foundation here. But the major difference comes in terms of gamma. So the gamma that we are going to substitute in this equation here is what will be a little different. I think this slide kind of explains it, but it's a little bit. Let me just get the simplified version. Okay, so here, the gamma we are going to use is called the gamma bar. We call it the gamma equivalent. Okay, because we try to estimate the effect of this groundwater level on the base of the footing. So instead of just using gamma 2, we will find an equivalent gamma that considers both. That is the unit weight of the soil below and the unit weight of the soil above, to find an equivalent value. And then there's a formulation that you can use. And that will be the gamma prime plus okay, so for case 2, this gamma, what you do, you have to substitute this into it, the gamma equivalent. And then how do we find the gamma equivalent? Is the gamma prime. So we know the gamma prime will be gamma saturated minus gamma W. So in our case, what is the gamma saturated? That is gamma 1. That's the gamma below the groundwater, right, surface, or the groundwater level, plus d over b. This is some sort of a gradient. So what is d? D is the distance from here, the base of the footing to the groundwater level. The distance from here to here is d, divided by b. Okay? And then you multiply it by gamma. Which gamma? The gamma 2. That is the one above. Okay? Minus gamma prime. So the gamma prime, we still use the same thing. The saturated minus the gamma W. Okay? So here, this part is a little bit more complicated because they are trying to estimate or find a function that can relate the effect that this groundwater level has on this footing. So the gamma formulation is a little bit more complicated. This is actually quite similar to what is there, but I think you can look at whatever you find easier to understand, then you go ahead with that. Okay, so any questions about this figure or the how do we find the Q, that is the stress at this point, and then how we find the gamma for this equation? Any questions?
And can you explain again why we need gamma equivalent in this case?
Oh, the reason why we need the gamma equivalent is because the water level here is not deep enough. It's like it's close to the surface that it can have an impact. Because although the water level stops at that point, but somehow it will affect the structure or the soil structure above it. So that's why we use the gamma equivalent. It has an impact on the overall stability of the foundation. So in case 3, you will realize that we don't use this because the depth of this is deep enough, so it will not affect the foundation. But because it's not deep enough, it has an impact on the foundation. So that's why we find the gamma equivalent. Because if you only use this, then you will overestimate the bearing capacity of this, which can be a problem. Okay. Okay, if no questions, we can just do a similar example and try to put the formulas we have to use. Is it okay if I erase this? No? Okay. Okay, so this is actually quite similar to the problem we just did, but in that case, the water level was here. So now we just move the water level a little bit lower, and then we try to solve the same problem. So in this case, here is E equal to 0.5 meters. Okay, so just like the previous one, the shape factors are all the same, like the shape, the depth factor, and the inclination factors are still the same. Nothing changes. The only changes we are going to observe will be in the evaluation of the stress at the base of the footing and then also the gamma. Okay, so similarly we can just do the same thing. So we want to do this calculation in first in terms of Q. Okay, the stress. So what will be the stress at this point? If we have the same problem, whereas this gamma 2, sorry, is 18. Okay, so if we are going to calculate in terms of Q, that is the surcharge at this base, right? So the Q will be what? It will be just this 18 times 1, right? So we just have 18, right? The same. And then we want to find in terms of gamma. So how do we find the gamma? We use the gamma equivalent, right? So that is the gamma prime. Okay. So in our case, the gamma prime will be the gamma saturated minus the gamma W, right? So that will be what? 20 minus 20 minus 9.81 plus. So what is the D in this case? What will be the value of our D? What do we substitute for the D in this?
0.5.
Yeah, 0.5. Because the D will be the distance from here to here, okay? So this D over B is some sort of a gradient, okay? So it will be 0.5 divided by B, okay? What's the B for the footing? It should be 2, okay? Then you input your gamma. What will be the gamma? Is the 1 up, right? The gamma 2, which is 18, minus gamma prime. Okay, so by just substituting here, we can get the gamma equivalent, okay? First we calculate the gamma prime, which is the gamma saturated, which is 20, minus 9.81, that is the gamma W, plus D over B. So the D from here to here is 0.5 over B, which is 2. And then you multiply that by gamma. What's the gamma? That's the unit weight above the ground level, which is 18. And then minus gamma prime. So which is the same like here, right? 20 minus 9.81, which is around 10.2. Okay, so you can see like even for the case one we did and the case two here, all the other factors still stays the same, right? So the only thing we need to worry about, or the only things that we need to pay attention to are these and these, okay? What gamma value do you substitute into the equation? And then what Q value, that's the stress that you need to substitute into the equation. Okay, so here once you get the Q, you get the gamma, and then you just do the same process to find all the other factors, then you just substitute into the equation, and then you can directly attain. Okay, so do you have any more questions about case two? Okay, and the final one will be case 3. So case 1 we said the water level is a little above the footing, and case 2 it is just a little bit below, and for case 3 the water level is all the way down. It's really far away from the base of the footing. Okay, so in this case, this df plus b is actually still less than the depth of the water level. So you can remember previously we said when we are going to calculate the Q in terms of Q, so if I'm going to find the stress at this point, I'm only going to say this gamma 2 multiplied by the depth of the gamma 2 multiplied by the depth of this. It's pretty much the same. We are following the same process, right? The same. But you remember in the previous one when we said in terms of gamma, for example, case 2, when the water level was a little bit below the base of the footing, we use what? gamma equivalent, right, to substitute in our equation. But now we don't need this because this water level is too far away from the base of the footing. It will not have any impact. So we still use the gamma above. Okay, we will use this gamma 2. Okay, so now here in the gamma is just equal to gamma. So this is actually the same as the previous ones we did before, like the dry condition, right? It's exactly the same. So in this type of problems, when the water level, the groundwater level is really deep, you don't need to worry about it because it will not affect the foundation. It has no impact. So most of the time, if you are given problems that deal with groundwater, typically it will either be case 1 or case 2 for the most part. For case 3, we just solve it like the typical dry soil condition. Okay, so for these problems here, case 1, case 2, and case 3, do you have any questions or anything you don't understand? Or anything you'd like to discuss? Okay, if not, we can just move. Okay, so this other case, this one is talking about the total stress analysis. And typically it's for saturated clay, when the clay is saturated. And it says it's only used for case 1, right? So we have the QU, and this is the equation, because the other one has already been eliminated. It is already 0. CQ, the N gamma is already 0. So the third part of this equation here is already gone. We don't need it when we are dealing with the undrained problem. So we only have this and this. Okay, and CU here typically is still the same cohesion. They use U because just to signify that it is undrained condition. Okay, and then this is also similarly the same problem. So you can see how we find out FC, the shape factors, the depth factors, and the inclination factors. They are all still pretty much the same. And then how do you find a Q? It's the same thing, right? 18 multiplied by 0.5, that's the depth, and then 20, that's the gamma prime beneath. And then you find this one, and then you also have the gamma, which is gamma 1 prime. That is the, because the footing is like this. Okay, so this is gamma 1, this is our gamma 2. Right, so the Q is just going to be gamma 2 multiplied by the multiplied by the depth of the foundation minus this, and then, so in this case that is, okay, 18 multiplied by 0.5. So here to here is 0.5 meters, and then here to here is 1 meter. Okay, so 18 multiplied by 0.5 plus. Now this one we use gamma 1, which is 20 minus, also multiplied by 0.5. And then the gamma 1, we will use the, which is the same, 20 minus 9.8. And then you follow the same process. Okay, so here, oh, sorry. Oh, this example is also the effective stress. So if we are going to do this part, the total stress part, if we are going to do the total stress part, then you don't need to subtract any water gamma W, right? Because it's total stress. It's like you combine both the water and the solid. So this part will be gamma 2 multiplied by 0.5 plus gamma 1 multiplied by 0.5. And then this gamma 1, you just substitute the same gamma 1. Okay? It's only minus gamma W when we are doing the effective stress analysis. That means we don't consider the effect of the water. But for the total stress analysis, you directly use the gamma values. You don't need to subtract anything. Okay, so the only difference here is that the equation becomes simpler because the m gamma is 0. Okay, and if you look at this figure, you can also notice why the m gamma will be 0, because when we are dealing with clay, the frictional angle for undrained clay is typically 0. So most of the time they will also not tell you that. Those are the two things you need to understand. For example, when you are talking about, they say dry sand, then you need to know that the cohesion is 0. In an exam, the professor probably will not give you that value. It's like, you should know that for dry sand there is no cohesion. They have no attraction, like the particles don't stick to each other. And then when they talk about the saturated clay that is mixed with water, the frictional angle typically should be 0 too. So in an exam, maybe they will not give you that value too. So those are two things that you need to know, like the difference between the cohesion and the frictional angle.
During the exam, will this table be given?
Yes, it should be given. If the table is not given, I think the formulations will be given, the formulas that you can use to evaluate these values. Yeah. But I think from my experience, typically they will give you a table to make it easier for you. Yeah. Okay, I think we can have a break, right? Yes, we can have a break, and then when we come back, we can continue. Okay, I think we can continue. The next topic we'll discuss will be talking about eccentricity. But before we start, I think maybe there are a few things that we need to play out, like maybe need to explain a little bit in detail for people to better understand. And one of the terms is like maybe the confusing terms will be effective stress and total stress. It can be a little bit confusing, but if you don't get a very good grasp of what is effective stress and what is total stress, then if you want to solve these problems, it can be quite confusing because you don't know what to do. So basically, when we talk about effective stress, we are only considering the soil. That is, we will remove the strength of the water. So for example, if I'm doing effective stress analysis, and I want to calculate the stress at this point, right? So let's say this is some gamma, this is some gamma saturated. For the effective stress analysis, if I want to know my Q at this point, right, what will I do? It's gamma times E1, right? Plus this because this is a mixture of both what? Water and soil. But we don't want to estimate the impact of the water in this situation. So it's effective stress. So we say gamma saturated minus gamma W, which is the gamma prime. Okay? That's the effective stress analysis. So that's the only major difference. It's like below the groundwater table, any analysis you do, any stress you find, for effective stress, you have to subtract gamma W, okay? But if we are going to do the total stress analysis for this problem, okay, if we are going to do the total stress analysis for this problem, and then we want to find the stress at this point Q, what do you think the stress will be?
Gamma times D1 plus.
Yes, gamma times D1, right? Because this is still above the water level, so we don't need to worry about that. It's still the same. And then now, how about here?
Plus gamma saturated.
Yes,
times D2.
so you say gamma saturated times the D2. So this is total stress. That's the only difference, okay? For total stress analysis, you directly use the saturated unit weight. That is the unit weight below the groundwater level. But for effective stress analysis, you have to use gamma prime. That means anytime you do a calculation that is below the water level, then you have to subtract the gamma W from the gamma saturated. That's the only two difference. So you just total and effective, basically that's what it means. Effective means consider only soil. Total combination of soil and water. So the same thing here. If this is case one, if they say the effective stress analysis, what do? You use this to calculate it. The same case one, if you want to find the stress at that point, what do? You use this one, right? Because they say total, that means you don't need to subtract the effect of water from that soil. Okay, is this okay for everyone? Okay. Okay, so the next topic we'll be talking about is the eccentricity. It's the eccentrically loaded foundations. So what does the eccentric loading imply? It implies that the loading is not at the center. So typically when we are dealing with problems like this, we have this, right? This, and then the loading Q is just right at the center, right? Right at the center. We typically deal with problems like that. Well, so far that's what we have faced. But in some instances, you have your footing like this. Okay, let's assume this is our footing. And then let's say the Q is still here. But we also have a moment acting on the foundation. If you have a moment acting on the foundation, the resultant loading on this foundation will actually not be at the center. It will shift a little bit. It will move somewhere. For example, for this kind of situation, we may have something like this. Okay, so for this type of problem, like let's say this is the moment on our foundation, and this is the loading. But if we want to visualize all of this as a loading, we just want to ignore the moment. You will realize that this distribution, this force will shift somewhere to here. Why? Because the foundation will be trying to rotate this way. So this will shift somewhere around here. It is no longer at the center of the foundation. So you will have this E. That is the distance from the center to the location of the load in here, okay? Q. And for this type of problems, we have different formulations and equations. Let's say, typically, you may have an equation like this, but in reality or in practice, mostly we will use this because they are easier to work with. So, for example, if we are dealing with a problem where for E equal SMB over 6, okay, so for this type of problem, for E, when the eccentricity is less than B over 6, so B will be here, right? The B is like this. Okay, when it's less than B over 6, then the Q max, the distribution of the loading will be like this. Why do we have such a distribution? You can just look at this formulation, right? This will be positive. QP max. This is how you calculate it. QB minimum. This is how you calculate it. So it's minus 1 minus 6 E over B. So if this value is less than B over 6, that means here we still have a positive value, right? This will be positive because this will be less than 1. So this part is still positive, but our QB max will be greater than QB minimum. Will be less, yes. And then if we have this, if E equal to B over 6, what do you think Q minimum will be? If the eccentricity is equal to B over 6. Zero, yeah. Right? Because now that this E, you substitute B over 6. So this becomes 1, and this is 1. So it's 0. So for that type of problem, when eccentricity is B over 6, the distribution is like this. You have something like this. Right? You have Q max and then Q minimum. The minimum will be 0. So they all follow the same formulation. But, okay, let's have a different scenario. This one is pretty common, quite straightforward. How about if we have our eccentricity is greater than B over 6? Okay, let's assume something like this. E greater than B over 6. So this is our Q. Okay, so if this value here, E, the eccentricity, is greater than B over 6, inside here we'll have what? We will have our minus, a negative value, right? So that means the Q minimum is negative. Okay, so when we are dealing with foundation problems, the positive value mean what? compression. We are dealing with soil. The positive means the soil is under compression. But in this case, your QB minimum now is negative. So that means it will cross here. It crosses the line, right? The QB minimum is QB okay, so this is the max, this is the minimum. So that means this part is under compression, it's positive, but this part is under tension. And we know that soil cannot take tension. Yes.
So can like the Q max and Q min become equal, so it cannot be the normal distribution? What condition it will have? I mean, in what condition of it, that condition will
Oh,
have?
you mean the Q max and the Q min won't be the same?
Yeah.
The only condition that can happen is if the loading is at the center. If this Q is at the center, but if there's a moment in addition to the loading, or the loading is not at the center, then it cannot be the same. Because if most of the loading is on this side, then you will have more load here than this side. Yeah, it's just, it's like that. The only way you can have a uniform distribution if the loading is exactly at the center. So the reason for this eccentricity is to take into account the impact of the location of the load on the footing. It's like it's not located at the center. Yes.
So like the Q is not located on the center, right?
Yes, the loading is not at the center. That, and mostly that is due to the moment acting on the.
So the difference between Q max and Q min is happen due to the moment, right?
Yes, yes.
So like one side tend to have more like force.
Yes,
you know?
yes, and then they can be calculated using this formula. Okay. So one side will have more and one side will have lesser. So, and typically you want this value to be E to be less than B over 6. If your E is greater than B over 6, this part is tension. So what does it mean?
The soil is under tension.
That means this side of your foundation is not in contact with the soil. This part is compression, right? So maybe this is your soil layer. Your footing will be more like this. Maybe something like this. Some part of the footing is not in contact with the soil layer. When this is greater than this. That's the only, yeah, because the soil cannot take tension, so it means they are not in contact. So when you are doing a design and this is greater than B over 6, you don't even need to continue. You go back. You have to restart from somewhere. You have to go back. You first calculate here, eccentricity B over 6. If the eccentricity is greater than B over 6, then you have to redesign or increase the B. And so when we are dealing with problems of eccentricity, let's say this is the area we have. Okay, so also typically when we are dealing with eccentricity problems or the loading is not at the center, you will find out that the distribution or the load is mostly focused on one area of the foundation. So it's like, typically when we calculate the area, we will say what? B times L, right? But in this type of situation, that is not the case. We have to evaluate the effective area. That is the area of the foundation or the footing where the loading is actually distributed on. So because of the eccentricity, maybe the distribution of the loading will be like from here to here. So this part will not have it. So if you are going to calculate the area, you will use B prime because eccentricity is along the B area. So it's like different, for different areas, the eccentricity is calculated in different ways. So you can see that, is it here? No. Oh yeah, here. Okay, so for this kind of problem, for bearing capacity on eccentricity problems, one thing you need to be very careful about is the B and the L that you will use. You don't, for example, if I say this one, the B is 2 and the L is 4. But there is eccentricity, and then probably the eccentricity is along the B direction, right? If I'm going to do any calculation using these formulas, then I need to find my B prime. So for example, that is here, one way eccentricity. So, but this one, for any problem, they will specify. Maybe they will say the eccentricity is in the B direction, okay? B direction or the transverse direction. Okay, so when we are dealing with eccentricity in the B direction, so that means the moment is acting along the B direction. Then, if we are going to use, anywhere we are going to use B, the effective weight, we have to use B prime. Okay? 2 minus the value of eccentricity. And then the L will still stay the same because the eccentricity or the moment is along the B direction, not along the L direction. Okay, so, and typically when you deal with this problem, they will specify, is it in the B direction or maybe it's the transverse, B or transverse direction. And then if the eccentricity is okay, and sometimes they will specify that eccentricity is in the L. Longitudinal direction. So it's probably L, or they will say it's L or the longitudinal direction along the longitude. So the effective width B prime So if we are doing the eccentricity check in the L direction or the longitudinal direction, then the effective width, thus B prime is equal to the minimum value between B, that is the width of the the width of the footing, or the length minus 2 times the eccentricity. Or, and then the next one, the L prime will be the maximum of B, and then L minus 2 times. So you can see these formulations are pretty much the same. And the reason why they write minimum or maximum is quite straightforward to understand if you think about it. Think about it. For example, maybe if I evaluate this, my L, if I calculate the L value may be smaller than the B value now. So now which one is the width, which one is the length? The shorter area need to be the width and the longer area need to be the length. So that's why you use the minimum of B and this value. And the L prime is the maximum, like the bigger one of the two. So for example, if I say the length minus 2e, but now that is smaller than the width, then this will change to the width, and then this will be my, or this will change to the length, and then this will be my width. Okay, so it's just simple, a very simple logic. Okay, so we have eccentricity in one way eccentricity in the B direction, one way eccentricity in the L direction, and then sometimes the eccentricity, like you have moment in both directions, on the B side and on the L side. So it's the same thing. For that type of problem, you can also use the same formulations. And then to calculate the contact area, when there's eccentricity, then the key is this. You have to make sure you use the effective values. That is the L value and the B value. That's the length and the width. Values that you are using have to be effective. They have to be the areas that are in contact with the loading. Because due to this moment, some areas of your footing probably won't have a loading. So if you are going to do any calculation, then you should only use the effective areas. That is the areas that actually are affected by the loading conditions. And here, another thing you need to remember is like up there, when you are trying to find the shape factors, the S factors, you need to use the what? You sometimes need to use the length and the width of the foundation, right? So when you're finding those shape factors, you have to make sure that you use these effective parameters. Okay, for example, they say B equal to 2, L equal to 4. And then you are trying to find the shape parameters, and then you directly use those values. B equal to 2, L equal to 4. Your solution will be wrong. Okay, you have to make sure you use the effective parameters, the B prime and the L prime. Okay? And then they will specify, like any question will specify whether the eccentricity is in the B direction, whether it's in the L direction, or it is a two-way eccentricity problem. Okay, so just looking at the formulations, like the eccentricity problems may seem like very complicated. So I try to summarize them in 4 steps that, if you follow, will make it easier for you to go through the problems. So number 1, the step number 1 is you determine okay. Step number 1 is that you have to you have to determine the eccentricity. So that will be E equal to M over Q. So that's the formulation, where M is the moment. Okay, the moment acting on your, in this case, that's the moment, and then the Q is the loading. Okay, and then ideally you want this value to be, you want your E to be less than or equal to B over 6, right? Because if it is greater than B over 6, that means that your foundation already failed. Okay, so the step number 1 is you have to determine the eccentricity. And then okay, so the next one, step 2, is that you have to determine the effective dimensions. So what does it mean by the effective dimensions? That's the B prime and the L prime, okay? So if the eccentricity, for example, our B prime is the width minus 2 eccentricity along the B direction, and the L is still L. Okay, so you determine the effective dimension. So if the question tells you that the eccentricity is in the B direction or it is in the transverse direction, you use this. Okay, you find where the effective, what is the effective width? Okay, because the distribution or the eccentricity is along the B direction, so you just use this. You determine. Okay, so when you are determining the effective directions, because we have two types of situations, right? Sometimes the eccentricity can be in the B direction, sometimes it can be in the L direction, or actually sometimes it can be in both directions. So let's also write the formulation when it is in the L direction. I have a lot of space, so. Okay, so this is the in L. In the longitudinal direction. Okay, so this will be the effective. Okay, and Okay, so the third step is that you have to remember to use the effective parameters to determine the shape factors. Okay, so when you are finding the shape factors, because you need to use the width and the length to substitute into those equations to get the shape factors right. So you need to remember to use the effective shape factor. So the effective shape factors are the ones you determine from here. That is this B prime and L. And then here, this B prime and L prime. So those are the effective shape factors. Okay, so before you substitute anything in the equation or you are trying to find the FQS, F gamma S, whatever, anything that has to do with shape, you have to make sure you use the effective dimensions that you calculate in part 2. Okay, if you don't do that, then your solution will be incorrect. And the final part, if we are going to, okay, it asks us to find the loading, the QU will be okay, it's also going to be the same. You have to use the effective. Okay. So just like in the previous part, when we talk about the forward pressure, we pay more attention to the Q, that's the stress, and the gamma. In this type of problem, we have to pay more attention to the effective shape parameter. So, any question about these 4 steps? Okay, so if you know, oh, then that's fine. Did you already upload this file on the Google file? Yeah, this is already there. Okay. So yeah, I think we will stop here for today. And then if you have time, you can follow the steps or the procedures we did today, and then try to maybe go through one or two problems on eccentricity. Then you will find out that it's also like pretty much similar to what we did previously, except that the shape factors change, like you see in FCS, FQS, F gamma, blah blah blah. It's pretty straightforward. I think if you understand what we did from 1, 2, 3, 4, it will be quite easy to go through these problems as well. Okay, so bye-bye.